I think that now we are ready to start the first workshop. Yay! So I'll invite Jordan to the stage.
Okay, so hey everybody, my name is Jordan. I am the, I guess, one of the founders and the CEO of Demergent Labs. We are a small team, 3 people. We have a grant from DFINITY to basically build 3 main projects. One is called Azle, which I'm about to show you. Azle is a TypeScript CDK for the internet computer, so you can write your canister smart contracts in TypeScript. Our other project is called Kybra, which is the same thing as Azle. It's just for Python. And then our other project is called Pseudograph, which is a GraphQL database. We're mainly focused on Azle and Kybra at this time. But our whole purpose is to just bring the languages you already know and love to the internet computer so you can just get started without having to learn too many new things. So first off, if you have any, if you want more information, Demergent Labs, our GitHub, is like the source of everything. So here you'll find our Azle project and our Kybra project, and it's all open source. Basically everything we do is open source. Azle and Kybra right here. There's a little bit of information in here. I just want to show you this examples directory. This examples directory is like just full of all kinds of different examples of basically everything Azle can do. So I highly recommend going here to try to find the things that you need. Besides that, we have the Azle book. Demergent-labs.github.io/Azle. And the Azle book is our attempt at a very in-depth guide to canister development in TypeScript. And Kybra has the same thing. If you're interested in Python, there's a Kybra book. So Kybra book, Azle book, the GitHub repos. Reach out to me on the Discord channel, the Encode one, or the Internet Computer Community Discord channel. We have a TypeScript channel and a Python channel, which aren't exclusively for Azle and Kybra, but generally speaking, they are. And yeah, so I guess I'll just jump in. We are just going to, start with some basics, build up from there. And we will have time for questions at the end. So just type those in. I don't know how you ask the questions, but just keep them in mind and we'll try to get to all of them. So, and if you're new to the internet computer, look, it's just a decentralized cloud platform. Okay, imagine something like AWS, something like Azure, but it's not owned or controlled by one company. Everything is replicated by default. You have a lot of really nice built-in security and scalability type features. And it's a very different blockchain, different type of computer than other blockchains. It has chosen a very specific set of, trade-offs and design considerations, which kind of gives it a lot of properties of the cloud, gives it some properties of blockchain. It's something kind of between the two. So you have to think for yourself, what properties you want from this and what's appropriate. One more thing right before we get started. I really want to point out that Azle is in beta. So as just a disclaimer, we don't have a ton of live, continuously operating Lindy effect type things. We have lots of tests, but we don't have the extremely in-depth testing that we want to do. We don't have security audits yet. And some of the software, like the core software we use under the hood, is also in this beta state. So you just have to keep in mind that it's a beta project. There could be unknown security vulnerabilities and such. So just keep that in mind. It's totally open. You can use it. It's extremely capable, but I'll just give you that information and then you can make your own decisions from there. So we are going to just start with a simple project. So pretty simple. You just need a terminal and VS Code. I highly recommend VS Code because obviously it's one of the best editors ever, but it also has very, very good TypeScript capabilities. And we're just going to use the npx command, npx Azle new. This will generate a very simple project for us. I'll just call it Hello World. I'll just add this to my VS Code. Okay. I might need to zoom in for you guys. So first off, notice it's just a very, very simple kind of node type project, very similar to what you're going to get with any other TypeScript project. We have our tsconfig.json. Generally, you should just kind of copy paste this. These are the settings that we have found to be most appropriate. You can always try changing them, but this is our recommended default for now. We have our package.json. Here's a bunch of scripts you can use if you want. You don't have to use these. And our main dependency right now is just Azle. 0.16.3 is the latest version. The dfx.json is the Internet Computer specific configuration file. Inside of dfx.json, you're going to define each of your canisters. And inside, this is the specific configuration that you'll need for an Azle project. Generally, you just copy paste this and change the names of the paths. It's not too complicated. Eventually, we will hopefully get it to something like this: type Azle, and something like that. It will be much simpler in the future, but for now, we are stuck with this. Not too bad though. And then here's our source directory, and from here on out, it's basically just TypeScript with some Internet Computer APIs. So let's get inside here, run npm install so we can get Azle installed. This squiggly should disappear momentarily. Okay, everything's installed, everything's perfect. This is like the most simple example you can think of. It's introducing two very, very important concepts here. First is the concept of a query method. If you mark your method with this query annotation here, basically what you're saying is that this is a read-only method, and that your canister, and by the way, canisters are the fundamental application unit. It's analogous to a smart contract, or I guess just a program or something on a AWS or something else. But your canister or your container, you can expose these read-only methods, and read-only methods return very quickly. So if somebody calls them from the outside world, and generally how do you call into these methods? There's an HTTP interface. You basically put the canister ID in there, and you can call in. And there's some very nice clients. They're called agents, which are client libraries that you can use to make this all very easy. So when you call this query method, it's read-only. It executes very quickly, on the order of, I don't know, tens to hundreds of milliseconds, very fast. And what's important to understand here is that these query methods, you can't persist any of your state changes. So if you have any variables, like this global message variable, if you try to change this message variable from within the query method, it will change temporarily. But as soon as that query method is complete, that change will be discarded. So query methods are very useful for things that you want to be read-only or want to return very quickly. The next concept is the concept of an update method. And an update method is not read-only. You can actually write. And this is kind of the core of the actual blockchain or replication process of the Internet Computer. An update method will persist changes, and those changes will go through consensus. And so all of the nodes that are running your canister will run the Internet Computer Consensus Protocol, and it's a BFT, Byzantine fault-tolerant protocol, and it will decide if they all agree or not, more or less. And if a sufficient number agree, then your state will be persistent. So if you look at this example, you can think of this as a very, very simple database. Here's the database. It's just this global variable. That's what's really, really cool about the Internet Computer, at least getting started. They have this concept of orthogonal persistence. So anything you store, in global memory on the heap is going to be automatically persisted for you. Okay, so that's our simple little example. Now let's get this thing booted up. First off, you're going to need DFX installed. If you go to the installation instructions in the Azle book, it tells you how to install DFX. Very simple. Basically just run this command. We are on the latest version, 0.14.0, latest stable version. You'll just run that command, get installed. I already have it installed. So I'm just going to start up a local replica. DFX. So DFX is the tool that we installed. Start will start your local replica. Clean will make sure it kind of gets rid of any previous state. It's just useful to do that. Oh dear. I can't believe that that just happened. All right, I'll start up here in this directory. So yeah, what we're doing here is just booting up a local replica. A replica is basically an internet computer node, more or less, running on your computer that you can deploy into. So I'm just going to leave this running in the terminal. And I'll go back into my project. And if you want to deploy your project, you just run, let's see, hold on. Oh, this is disturbing. Unknown variant Azle connected one of Motoko Rust assets. Oh, I must have messed up my, aha, there we go. Okay, DFX deploy is going to basically build and compile your project and then actually deploy it to the local replica. Azle takes a few seconds. The initial install takes a long time, which I've already done, but the subsequent installs are pretty fast, generally speaking. There's two ways that we can interact with this canister. One is on the command line. So I can do DFX canister call. My canister name is hello world. And I can call any of these methods. So get message, it's just an empty string, there's nothing there. Set message will allow me to actually pass in a property or a string. Hello world. Takes a little bit longer because of consensus. And then if I call get message again, there it is. So command line is great, especially awesome for testing, automated testing, such. Or there's this really nice UI thing where it's going to automatically generate this stuff for you, and then I can do stuff here. A new message. Go and see it's changed right here. Okay, so that is the basic, more or less installation process. Get DFX installed, boot up your replica, get an Azle project, or most of what I just showed you is the same for Motoko, Rust, and Python if you want to do those. So nothing crazy, you just want to use the DFX tools to get started. Notice that this candid file, it's a .did file. This is the interface definition language of the internet computer. It was automatically generated for you from your source code. You'll get to know, I guess, how important the candid file is. It's what allows canisters to very easily communicate with any other canister. It allows clients to communicate with any canister written in any language because they share this common interface definition language. Okay, so let's start stripping this down and make things a little bit more complicated. So let's start like building up a database here. So instead of just one string, let's actually make a general purpose key value store. The keys will be strings, the values will be strings. Notice I'm just using normal TypeScript types here, and it's nice because it's going to show me what's wrong and what's right. Let's make a simple getter where you pass a string in, and it will return a string. So it's simple. I'll just access the database at that string. And let's make a simple set function where you can pass in a string key and a string value. And yeah, we'll just set key at the key to that value. There you go. It's very simple key value database. We'll just deploy this. And what's fantastic about this is that, if you actually deploy this to the live internet computer, this is a database that's just running. It's available. And yeah, you got keys and values. So let's say key 0, what's going to happen? Well, it has this crazy error because we didn't handle the case where DB key doesn't exist. It's expecting a string, but we returned undefined, and so we didn't handle that, so it's breaking. But let's maybe set key 0 to the string 0 and try it again. There we go. Cool. Another one, so key 1. Okay. I mean, yeah, it's a general purpose database. Getter, setter, nothing crazy. Let's actually take care of this problem here. We're going to import the opt type. So Azle follows the lead of Rust and Motoko and Candid by embracing a concept called algebraic data types. And it's a little bit more of an advanced topic, so you can go study it elsewhere. But basically, the idea is to remove, generally speaking, the concept of like null and undefined and make everything, I guess, quite explicit. It's a very enum-like experience. So an opt can basically have one of two values. It can either have something in it or it can have nothing in it. So instead of returning a string, we're going to return an opt string. And we're going to grab the value out of the database. And basically, if the value is undefined, well, I'll make it easier. If it's not undefined, we'll return opt.sum, put the value in. If it is undefined, we'll return opt.none. All right, so now we will handle it appropriately. And then down here, I think we're still good. So let's deploy that. Yeah, this is probably a very foreign concept if you're a TypeScript JavaScript developer, but it is relatively simple. If you have something, you say that you have something. And if you have nothing, you say that you have nothing. All right, it's been deployed. All right, notice our type has changed. It's now opt text, and notice that the candidate file is always being kept up to date, which is really nice. So now let's try to get something that doesn't exist. So, and by the way, the state of your canister, if you store things in global variables, like just on the heap, every time you deploy a new version, basically, it's going to wipe all that state. And later, I'll hopefully be able to show you how to avoid that. So our database has been wiped. Let's try to get key 0. Okay, this time, I know I said it gets rid of the concept of null. In Candid, it still says null, but it does have the opt type. So that's a lot nicer than throwing a crazy error. And then obviously, if we set the key, now we'll return an opt 0. So, and this highlights a concept. This Azle library, I mean, this has all the types, all the annotations, at least a lot of them that you'll need. And this opt type, by the way, is a Candid type. Candid, like I said, is the interface definition language. Those are the types you're going to be using when you try to expose things. For example, parameters, return types, things like that. Anything that needs to be serialized or deserialized by the platform, you're going to want to embrace the Candid types because all that serialization is done automatically for you. Okay, so yeah, we got a simple key value database here. Let's increase the complexity of this a little bit. We are going to introduce another Candid type called a record. The record is basically your object, your data object, your table. It's your basic complex data type on the internet computer. So let's introduce a new record called a user. It has an ID, which is just a string, and then a username, which is a string. And then to show you maybe one of the number types, let's grab like a nat32, maybe for age. And let's change your database. We're going to make this more like an actual database. So it's going to have a user's property, which is going to have keys, which are strings, and values, which are users. And then down here, our database is incorrect because now it requires an empty user. So there we go. Nothing crazy here. Now when we get something, it should be a user. And now when we set something, and let's say ID here, we're going to grab it from users. Okay, that should all be set up now properly. And then we'll simply pass in, now to make it easy, we'll just pass everything in. So the ID, the username, and the age. And I feel like it's usually good practice to actually return the ID even though we're passing it in. So we'll just construct our user. And then we'll set our user, and then we'll return the ID. Okay, so now our database is starting to be fleshed out a little bit more. We'll deploy that, play with it. Nothing too crazy. We just introduced the concept of this record type and just started making our database a little bit more capable. Should be deployed any second now. All right, so again, let's try to get a user. Doesn't exist. So let's create a user. ID 0, username, lastMGS, age 32. Nice, returned ID 0. That means it worked. And boom, there's our user. Pretty sweet. And we can flesh this out with maybe another query. Maybe something that just returns all the users. For that, we'll need our vec type. And we'll just return all the values of db by users. As you see, it's very flexible. I'm just using, I am using these candid types, but generally speaking, it's pretty simple TypeScript and JavaScript things that you probably are already very used to. Okay, there are no users, but again, let's set user up, and then we should have one user here. Sweet, there it is. Awesome. And if you want to get the keys, you could do that. And if you want to create more complex filtering and stuff, you can create functions that provide filters and everything. That's what our pseudograph GraphQL database does for you. Once we revive the project, it's going to do all this crazy database stuff for you. But for now, if you are just making something basic, you can do that. Let's show you. Yeah, let's use an npm package. So it'd be pretty cool. So let's get an ID working. So see here how we just pass this ID in, right? Ideally, the canister would be able to generate a random ID for us. And there's a few ways we could do this. We could kind of create like a custom function that does it for us. We do have randomness available. Or we could use something like the UUID npm package. That's another way that we could do it. To do these things, though, we really need some randomness. So let's introduce the concept of a cross-canister call. So right now, everything I'm building is inside of a single canister. But what happens if you want to communicate with other canisters on the network or communicate with some more advanced functionality of the internet computer? So the first, probably most important canister that you will interact with is called the management canister. The management canister is a virtual canister. So it's not like necessarily a canister actually deployed, but to you, it seems like a canister. And you interact with it just like you interact with any other canister. So here's what we're going to do. The management canister gives you pseudo randomness from the Internet Computer Protocol. So a very, very high quality source of randomness. So what we're going to do is we're going to create a function. This will be an async function because we're doing cross-country calls. All cross-country calls are asynchronous. I'm going to get some randomness. This will return a blob. Oh, and wrap that in a promise. Okay, so we're going to store our result in something called result. And Management Canister has all this stuff available. We'll go through some more of that later, but we're going to just call a function called rawRand.call. And this promise will get kicked off, and then asynchronously, the result will be here. Like I said, we embrace algebraic data types. So we're going to use a special function called match. That's going to make it really easy to get the result out of this. So we're going to match on the result. And this is a result, like an actual algebraic data type result, which means it has an OK property if everything was OK. It has an error property if there was an error. I'm going to import the IC object, which has a lot of nice utilities for you. And we're going to trap if there's an error. Okay, let me deploy this and I'll explain. So here's our first cross-canister call to the management canister. This result's going to come back. The Internet Computer does guarantee that you get a result, I believe. But that doesn't mean that the result, that there was no error that occurred. So what we're going to do is we're going to make sure we handle basically every possibility here. And there are only two possibilities for a result. A result can either be OK with the actual resulting value, or it can be error with the actual error. So we just handle both cases. If it is OK, it's going to have our blob. A blob is a uint8 array, and we're simply going to return the blob. If there was an error, it'll be a string, and we'll call ic.trap with the error. And a trap basically ends execution right at that point. And more or less the state that has occurred. It's a little caveat with the cross-canister call, because state before the call will not be discarded, but state after the call will be discarded, and it will stop, show the error, and undo changes up to that point, basically. So we should have our get randomness call here. So let's give it a call. And in this case, there was no error, and it returned, I believe, 32 bytes of beautiful randomness. And if I call it again, I should get a different set of bytes. Yep. So that's pretty awesome. So now that we have this randomness, for example, we could store it up here. Type blob. I'll give it a default value. And when this comes back, not only will I return it, but it'll actually store that randomness globally so that I can take advantage of it. And then you can take that randomness and basically you could take like a SHA-256 hash of that and create an ID. So let's show you how NPM works. Now, not all NPM packages will work. There's a lot of APIs that don't exist yet. This is not Node. This is not the web. It's something much more bare bones. But we hope to start plugging those APIs for you as time goes on. But some things do work. So I know for a fact that JS SHA-256 works. So I'll go import that. And there we go, a little hash library. I'll just make a little query method here. Random hash. This will return a string. And let's just basically hash the current randomness that exists. This is building our way towards one solution for generating a random identifier. Not too bad. Okay. All right, here's random hash. So there is no randomness right now, so I don't know what will happen. That must be maybe a hash of empty string or something. If I call get randomness, it should return the randomness and store that randomness in that global variable. If I call this random hash, it should be different now. Sweet. Every time I call get randomness, I should be able to produce a different hash. Sweet. There we go. That's nice. I mean, to really hook this up, yeah, I mean, basically showing you how to store randomness above would be useful for probably some other things. So at least you know how to do it. And let's hook this up here. So we're actually going to make this whole function sequence. We're not going to pass the ID in anymore. Instead, we're going to generate the ID, which will be a SHA-256 hash of, and we're going to call our getRandomness function right here. And I think that'll work. So yeah, it'll go get some randomness, hash it, and then that'll become the ID. So I didn't try this exact path before, so let's see how it works. And then we'll move on to showing you some more functionality on the management canister, which will be very important for Bitcoin, HTTP outcalls, and threshold ECDSA. But basically what I'm showing you is how you're going to access all that functionality. Okay, so now when we create a user, so set, I only pass in the username and the age. If all goes well, it should return a user with, yeah, sweet. So here's the ID that it generated. And then if we go get that user, oh wait, no. I have to grab this ID. There we go. And there we go. There's user, age 32, username, last name, yes. Okay, that's one way to do it. Not the best way because you have to do a cross-canister call to the management canister to get that randomness. But there's a few other ways. For example, you could use the UUID npm package. Problem is that we need to do a little bit of work to get that randomness hooked up for you automatically. But yeah, we're working towards polishing things like that. But you have, I guess, a lot of options here. You could also use math.random and create your own, you could create 32, an array of 32 values using math.random and hash that as well. That maybe would have been easier. There's a lot of options. Okay. So yeah, I mean, there you go. This is a very simple example showing a few concepts. Let's make this a little bit simpler. Or I guess we'll just go down here. Let's show you how to start accessing, like I said, Bitcoin functionality, TECDSA functionality, etc. So let's start with TECDSA. So if you're not familiar, ECDSA is a very, 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 very popular and well-used public-private key algorithm that allows you to generate public and private keys and to produce signatures on them. Ethereum uses ECDSA as its main signature scheme, and so does Bitcoin, I believe. And that is really the base of the Bitcoin functionality on the intercomputer, is being able to generate these threshold ECDSA signatures. Like the protocol itself will generate these for you. Generally speaking, so if you didn't have the T part, generally speaking, you have to generate a public and private key pair, and you have to store that private key in one location, which is obviously a very large point of centralization, and which can be very dangerous. So the T part here means threshold, which means there is no one private key stored on one machine or one device anywhere. The key essentially is split up into shares and shared amongst nodes in a subnet. And what's cool is the intercomputer lets you access this functionality and lets you use these things. So let's see what it's like to get one of these key pairs. So again, we're going to use the management canister to do this. And it's all under ECDSA. We're going to basically say, give me an ECDSA public key. We're going to call that, and then we need to pass in some options. First option is canister ID. We're just going to say opt.none for that. it will default to our canister in this case. I'm not exactly sure what the canister ID option here does for you, but you are able to set that. By default, it'll just be our canister ID. Then the derivation path. Basically, it's just like kind of a, as I understand it, BIP32 type thing where you can derive many different key pairs from basically like a master key. So in our case, we're going to set this to empty. So we're just going to have one key, I believe, for our canister. And then the final thing here is the actual key ID. And in our case, only have available to us, I believe, the SEC P256K1 curve. And the name, I forgot the name, so let me go look it up. But basically, we're going to use like the test key. So you have to choose the key that you're using. In production, I believe the key will be different than the one in development. Let's go see this example. DFX test key. There it is. Okay, so basically this is going to generate a key for us. And now we're not going to get the private key because it's stored threshold by the nodes, but we will get the public key, which will basically be a blob. So again, we're going to match on that result. If it's okay, that means we have our blob, and we'll just return it. Oops. If it's error, then we have an error. And again, let's just keep it simple. We'll just trap on the error. Let's see what the problem is. Oh, yeah. So we have to grab the specific public key from there. Okay, so let's deploy that. So yeah, I mean, that's basically it. You can play with the canister ID option and the derivation path for your app. And in production, you believe you'll change this to different key, but it's the only curve that we have currently. And again, you just do a cross canister call to the management canister, and you should get your key out. Okay. All right, TCDSA, here we go. Let's generate a threshold ECDSA public key. There we go. There's our key. If I'm not mistaken, if we call it again, because we have no derivation path, we should get the exact same key. Yeah, these look the same. Okay, once you have that key, then you can take that and basically start formatting it appropriately for Bitcoin or for Ethereum or whatever you need. It's just bytes here, but follow whatever algorithms. DFINITY has some sample code that shows you how to do this in Rust and Motoko. We'll be working on that same sample code, hopefully to get out to you very soon. Hopefully we'll have the correct NPM libraries that you should use. If not, we can create some Rust plugins that allow you to have the same functionality. But yeah, this is the base, TCDSA. And then we're kind of running out of time, but it's basically the same concept for anything else you want to do. So let's just show you what's on the management canister. A Bitcoin get balance. What are the options here? You pass in your Bitcoin address, the min number of confirmation that you want to wait before I guess it would even consider it valid. And then whatever network you're on. Are you on the test network? Are you on the live network? So that's how you can get Bitcoin balance. And there's only really three things, or three or four things here that does get current fee percentiles. That will help you, I believe, just set, monitor the fee conditions of the network so you can set this appropriately. Get UTXOs. Imagine this will simply take, again, an address and a network, and then you can play with that filter to see what that does. And then finally, send transaction. So send transaction will actually allow you to submit a transaction to the live Bitcoin network. No other functionality is needed from you. As long as you format the transaction. Notice it just takes a UN data array. So basically just a blob. You are responsible for formatting it appropriately, producing a signature, and submitting that. And if you want to produce a signature, on a well-formatted transaction, then you would just call sign with UCDSA, and yeah, basically pass in the hash and the derivation path that you use, so it knows which key to use, and probably the exact same key ID and stuff. So yeah, that's the basic cross-canister call functionality for the management canister, at least. And now in the last few minutes, let me show you if you want to talk to other canisters. For example, everything we've shown you so far is in a single canister and using the Bitcoin functionality. But what if you want to connect to the ICP token, which is its own set of canisters, or the CKBTC token? So like I said, this functionality I just showed you is like core Bitcoin. Like it really is communicating directly with the Bitcoin network, and you're using threshold ECDSA to sign actual Bitcoin transactions. So you're going to have the same, you're just going to be limited by the throughput and all the rules of the Bitcoin network itself, which has its advantages and disadvantages. So the Internet Computer has introduced a new token called CKBTC, which does use all the stuff I just showed you under the hood to lock Bitcoin inside of this canister, basically. But it issues an Internet Computer native token on top. And if you want to access that functionality, there's a couple options for you. One is you can import the ICRC canister. So let me just show you how this works. Just call it test for now. Okay, so this is a canister like the management canister. Notice, sorry. You have to make an instance of this. So basically, I would make an instance of ICRC, and I would pass in the identifier. Let's import principal. Principal is available from Azle. This lets you. This is how identifiers are essentially done on the Internet Computer. And you would go find the live or local ID, the canister ID, the principal for the CKBTC canister, and here's your instance. And once you have your instance, you should see all the ICRC1 methods on here. So transfer being the most important, that'll let you transfer tokens, and then you can check everything else: total supply, symbol, name, all that stuff. That's one way you should be able to use the CKBTC canister because it is ICRC1 compliant. But another way is to use the ledger canister. The ledger canister is ICRC1 compliant, but also has some extra functionality. For example, I believe being able to look at blocks and transactions. And so if you wanted to use the full ledger instead, it would be a very simple concept. Should just call it CKBTC. This is now an instance of the ledger canister, and it's basically the same thing. It's just has some more methods. So we have some legacy stuff, account balance. We have archives, canister ID, decimals, and then again we do have the ICRC1 methods on there as well, etc. So yeah, I mean, I feel like this is a very good stopping point. So I'm happy to take questions.
Cool, amazing. Actually, Dominic has been very active in the chat for the last hour, and he's answered, if not all, then most questions. But if you want to ask Jordan a question, you can just type them in the chat right now, or you can use the questions tab right next to the chat. Yeah, I guess one of the different themes that's been going on in the chat for the past hour is why do you have to use Azle to build a project, and if not, would you recommend anything else, or what are the benefits of using Azle as opposed to coding in Motoko?
The benefit is that it's TypeScript. There's millions of TypeScript developers. Lots of people already know TypeScript. TypeScript and JavaScript are basically tied with Python as the most popular language in the entire world. There's multiple decades worth of material out there and information. You could write your front end in TypeScript. You could write your back end in TypeScript. All the reasons you'd use Node.js for the back end, and it's the same exact concept. So that's why. Like I said, it is in beta, and there's going to be some trade-offs. Biggest trade-offs right now would be the performance is much less performant than Motoko or Rust, but I'm pretty sure within a few months, we're doing some experimental stuff. It's going to take a lot of work, possibly, but we're thinking that performance gap is going to possibly drop to near zero. It might be just as performant as Motoko or Rust, or at least very close soon. So we will see about that. If you Motoko and Rust, I could especially recommend Rust. Rust is very mature. Rust has many libraries you can already use, and DFINITY uses Rust for many of their system canisters. So yeah, it just depends, I guess, on what level of maturity you are okay with.
Yeah, and to build off of that, Jupes is asking how much less performant is Azle currently against Motoko?
It's very hard to say for sure. It really depends on a lot of things, but our best guess would be, like, translating to actual cycle costs, it might be 2 to 4 times more expensive. If you look at instruction costs, it's like multiple orders of magnitude more instructions sometimes, like 100 to 1,000 times more. So that's the current state, more or less.
Cool. Artem is asking, when ICRC versus ledger canisters are recommended, what are the most appropriate usage? What's the most appropriate usage for each one?
I think it probably doesn't matter too much. Like, my guess, because I haven't done these things in production yet. We're just kind of building all the interfaces and all that stuff for local development. But my guess would be use ICRC if all you need is ICRC, as in if you only need those methods, you're fine. If you need the extra methods that the full ledger gives you, you can go ahead and use that. But it probably doesn't matter. If you use either one, it'll be very obvious to you if it's not appropriate, because you won't have the functionality that you need. So to keep it simple, just use the ledger and you'll be fine. That's probably the actual answer.
Cool. We got one more question by Armando, who's asking, he wants to confirm, actually, speed-wise, is Rust the fastest, and then Motoko, and then Azle and Kybra?
It's hard to say between Rust and Motoko. It seems like Motoko is faster in some cases, but it might depend on how much you optimize the Rust code. So I don't know. Rust and Motoko are neck and neck. I mean, I would guess Rust is probably, considering all circumstances, going to be the fastest of all the languages. But the benchmarks I've seen do show Motoko excel sometimes, or maybe most times. So
cool. I guess that answers the question. One more that just came in is, you mentioned heap memory. What is stable memory in Azle?
Yeah. Maybe to answer that, I could just share my screen again, because I could show real quick. Yeah, we didn't actually get to stable memory, but if you want stable memory, basically the easiest way to do that is to import the stable B-tree map from Azle. Then you can just create a new stable B-tree map, give it a memory ID, give it a max size for your keys and a max size for your values. And then you put your types in here. So string and user, for example. So there you go. This is how you could do basically this database, more or less. This part of the database, this is now stable. And this stable B-tree map will persist across state changes. You don't need a post upgrade, you don't need a pre-upgrade. It's just going to automatically do this for you as you write into the stable map.
Cool. Awesome. I hope that answers the question. And the final one, do you have any... Okay, Dominic is actually answering this one. regarding documentation for Motoko, but yeah, that's it. I think that's it, unless you guys have any more questions. Cool. I guess we'll wrap it up. Well, thank you very much, Jordan, for joining us both for the launch, and thank you to and for the workshop, and thank you to everybody else who joined us today. And can't wait to see you what you build in the next couple of weeks. And see you tomorrow for the next workshop. See ya. Goodbye.